started out with those carbon petals, and in this case we use hydrothermal synthesis. I know some people here are doing hydrothermal synthesis. Here's our soup that we put into the reactor, and we end up autoclaving this for an hour and a half at 135 degrees C. We dry it, and then we measure the surface area. So we did a BET surface area measurement. We talked about that in yesterday's lecture. What comes out are these needles, and the interesting thing here is we used a technique that I also mentioned, EDX, energy dispersive X-ray, right? And so we use that to map out the elements in these needles. Okay, and I know it's a little bit hard to see, but the panel E here is just a TEM image or SEM image. Panel C is the carbon, so I can actually see the elemental distribution there. Why do I care about seeing an element? Well, we weren't sure when we made this whether the nickel, cobalt, manganese, and oxygen were uniformly distributed in the in these needles, or if there was some kind of a core shell structure that was created or some sort of phase segregation, and so we wanted to map it out. So we get to green. Green is cobalt, blue is nickel, and cyan is manganese, and you can see that all of these look like it's pretty well distributed. So we have concluded that these elements are uniformly distributed in the needles, which is important to us, right? We would not want to have something where we had some phase segregation that we were not able to control. And then you see also that oxygen is everywhere. We can also get an idea from EDX of the relative amounts of the different materials. So in this case, our best estimate is that it's 5 parts nickel, 5 parts cobalt, 1 part manganese, right? Not an unreasonable type of distribution for what we've done. I've already mentioned that we grew our sample on these petals, so I won't belabor that point. I've already told you how we do it, but I want to remind you that, again, we're using these processes. This is a plasma chemical vapor deposition process, for example. Here's a chart that summarizes the overall performance of the device, and I think it's important to note here, and you'll see this CV curve later, that is not nearly rectangular. I told you that rectangular was the perfect double layer capacitor, and this is not nearly so, right? That's okay. We kind of wanted it to be that way, and I'll tell you why later. But we also did, we looked at voltage, we looked at charge-discharge curves at different current densities, so not just one current density. A lot of questions, by the way, in between lectures, which I enjoy very much, are, people will ask, should I use this voltage or that voltage, or this current or that current in my test? And my answer is generally, you should use them as many as you can. Do a distribution until you start to see a change, and then try to explain that change. We also have down here a specific capacitance for different current density. So as I said before, if you start to charge or discharge your device faster, it will potentially be manifested as a reduction in your capacitance, right? We don't see very much of that, only in these very, very low densities, but this was nice to see. It's a very, very high level of specific capacitance, and we can do different experiments. So in this case, we did control experiments where we had a double hydroxide with petals. That's in the red. And we also did the nanoneedles on carbon cloth without the petals at all, right? And so when you do these experiments, you can do a lot of different control experiments to compare to what you really are most interested in. But doing the control experiments can tell you things like, oh, what was the effect of the petals? Because if you go from the black to the blue curve here in panel C, that's the only difference is that one has petals and the other one doesn't. And so the petals are important here. They probably mostly are increasing total surface area because they're giving more area to grow nanoneedles on. So I have more nanoneedles in that case. Right? So this is an important thing to be able to do, but I'm showing you all the different techniques that we use in the lab and that we discussed this week. So some other electrochemical characteristics here, some lifetime. It had very good cycle life, at least compared to batteries. It has a power And the Ragone plot is interesting looking, right? It's very flat in energy density. In fact, so as we increase power, I'm not seeing that drop off, right? Which is really important, and I'll tell you why in a moment. And we also had our EIS, right? And so we had this Warburg analysis that we could do. The Warburg Effect is one that has to do with the diffusion of mass, the mass transfer effects, diffusion, and to some extent reaction kinetics in your Faradaic material, your pseudocapacitive material. So one thing that you might ask is, especially looking at that CV curve, you might ask, is it a battery or a supercapacitor, right? Well, there's two schools of thought right now that I can tell. The American Chemical Society's position is summarized in based on a paper that came out in Science last year, and the American Chemical Society looks at this CV curve, which is not nearly rectangular, and they say that this is a battery. It must be. This is what a battery looks like. This is what a battery CV curve looks like. Okay. Now, the Royal Society of Chemistry has a different perspective that's summarized in the paper that's listed here. And they look at the Ragone plot and they say, this thing is not tailing off in energy density as you increase the power. These are both very, very respectable numbers. It's not like we only use low power. And so they say it functionally looks like a supercapacitor, right? And so I don't know. I'm not going to get into a semantic argument with any of those very powerful organizations, the Royal Society, American Chemical Society. I will just tell you it is a pseudocapacitive material. And if I had to pick, I would pick the word supercapacitor for it, because supercapacitor has implications about function, especially to me. I'm an engineer, right? And so the function here of a supercapacitor is preserved, even though the details of some of the electrochemistry and the redox behavior looks more like a battery. And the reason that this one isn't fully a battery is that it's nanostructured, and so that's what makes it really fast, right? It's kind of a chunk of hydroxide material that is slow responding. The nanoneedles themselves make it fast responding. And so it makes it look like a supercapacitor. And those nanoneedles are really important, I think, in the function of this device. So we were surprised to find that when we looked back, we took an SEM image right after we grew the material, and then after 3,000 cycles, and we can't see any salient difference between those two. So what's happening as these things are reacting and then reacting again upon charging and discharging, what's happening is that these needles allow for growth, chemical expansion during the charge and discharge cycle, whereas and they have room to do it because they're isolated high aspect ratio structures. Whereas if they were in some sort of a jammed granular configuration, they'd be pushing on each other like a normal battery electrode does, and slowly decrepitating, forming cracks and so forth. But these aren't, right? So I think this is a crucial part. Of course, it also has ultra high surface area. Those nanoneedles have tremendously high surface area relative to their weight. Oh, let me go back quick here. I also wanted to show you when we turned the device into a two-terminal asymmetric device. So on one side we had the nanoneedles, and on the other side we had just a carbon electrode. So this was, the hydroxide was the cathode, the all-carbon electrode was the anode. And then we did a CV scan on that. Now we start to look more rectangular. And this has to do with the fact that we're adding, on the carbon side, we're adding a double layer capacitor to it. We still see some redox features, right? Shoulders in the curve. But now this is really a hybrid or an asymmetric structure. I'm not sure whether you'd call it a hybrid battery supercapacitor or a asymmetric supercapacitor. It gets back to whether I want to satisfy ACS or RSC. I don't care. But the point is that I have a more rectangular type of CV curve when I make this hybridization happen. Temperature effects. So now you see that we actually have better performance as temperature increases, right? And this is again with the two-sided device or the asymmetric device. We also have a relatively low IR drop at all temperatures, but we see the capacitance per unit area rising. Probably what's happening with that increased capacitance as temperature increases is that we're accessing more and more of the pores in the material, at the nanoporous structure. The electrolyte's becoming less viscous and it's able to penetrate. And then we do also some EIS on this device, and as it gets cold, you start to see that we're having more resistivity in our material, and we start to see a clearer feature of that semicircle start to show up, right, in this kinetics controlled regime on the left side of the curve, the high frequency part of the curve. So for me, as I move ahead, we'll be making more and more of our pedal material. I mentioned that before. This is our roll-to-roll system. We're really excited about it. We're looking forward to not just making small lab samples, but making samples that can go into very large-scale structures. I'm going to skip that slide. I'll just close with some thoughts about this particular topic. Thermal effects are really important to include. I hope that in the laboratory you will take the time to conduct some of your tests at different temperatures. I also have a book. I'm not hawking a book or trying to sell you a book. I'll send you PDF files of the chapter since this is an educational meeting that was published this year on thermal effects in supercapacitors. It's a short book, more like a monograph, but it has a lot of literature review in it, if nothing else. We also showed in the middle panel here that these nanostructured triple hydroxides are materials that could be high performance. I also should note that we compared to, and I briefly mentioned it, to double hydroxide, so to nickel cobalt. But the performance of nickel cobalt was far less than that of the triple hydroxide. We don't understand why. I mean, you could say, well, maybe just keep on adding more and more transition metals and you'll get better and better performance. I don't think so. But what I do think is that that the triple hydroxide provides a greater diversity of redox states, because these are all redox type reactions that can balance out with each other throughout the energetics of the reaction process. And so that's probably what's happening with the triple hydroxide. If I were you, there's lots of young people in the room here, I would be thinking about materials. If you're interested in supercapacitors or batteries or fuel cells, think about something that scales up. Whatever it is, think about something that scales up to the human scale. Spend your time and attention. Do all of the characterization. Do your material preparation, your material characterization, your device characterization carefully. Take the time to do it, and then go and tell the world about it. So with that, I thank you. It's been a wonderful opportunity for me to talk. Here's a picture of, well, on the left is my feelings for you expressed in carbon nanotubes. And then on the right is a picture of my research group back at Purdue University. So I thank you again, and I'll be happy to take questions now. Yeah.
So, wonderful nano needles. Have you tried to align the needles in front and opposite direction to make this?
To make like interdigitated needles. Yeah, I haven't tried, and of course it's happening in a bomb reactor, and so I don't know if we can get into to do that in an autoclave type hydrothermal process, but. Yeah, it's possible to do. We think that we're pretty happy with the fact that they are somewhat ordered in the way that they grow out of the system, meaning the spacing between them is pretty similar from place to place on the sample. But whether we could interpenetrate them, I'm not sure. Yeah.
By that geometry, I think we can increase again the capacity.
Yeah, it would be huge. Yeah, it would be like an interdigitated capacitor. Yeah, very good. Yes?
How do you decide the percentage composition of different metals in the triple hydroxide?
Yeah, it's a good question. For the most part, we didn't design the composition of the metals in the hydroxide. It came out of our process. And so we think that this is probably not quite optimal. We think that we probably should add some more manganese and try to get it. But I will tell you what happens in the process if you change, so there are lots of other practice processes that we tried before we got to this point. If you change the pressure or really change the temperature or amount of material that you put in the reactor and the temperature, you can get other morphologies. So we got a lot of these nanowalls or sheets instead of the needles in many cases. And so the needles are, I think, what gives the most uniqueness, the highest surface area. And so changing the chemistry also changes the morphology. So you have to kind of find the right way to do it. So what we're in the middle of doing is a designed experiment, right, where we're varying